Alright, this is my project, and I am examining the data relationship in the wastewater treatment between nitrogen and ammonium. And so, wastewater is defined as anything coming out of sewer pipes and into treatment facilities. They can come from many sources, from domestic sources such as homes and apartments to industrial. They can also come from other sources such as storm runoff and medical waste too. We'll focus on the specific treatment called anaerobic ammonia oxidation treatment method, or known as AMOX. AMOX uses ammonium to treat wastewater with excess nitrogen. Specifically, uses both nitrite and ammonia to produce nitrogen and dinitrogen and water, and so it'd be used to remove excess nitrogen in certain types of wastewater. And using this method, we can improve energy and cost savings, but construction costs are still pretty high. And so the research question is there a statistical relationship between the amount of ammonium added and the amount of nitrogen removed using this method? And this will be proven using the model simple linear regression, or SLR. So the data is coming from the textbook, and the data is a sample of 120 wastewater samples from a wastewater source from producing dry spun arsenic fibers. This is a highly toxic wastewater with lots of excess nitrogen, and we are testing to see if there's a change of nitrogen removed based on the amount of ammonium added. And so this is our part of the data from the file. And so, moving on. So in order to use the SLR model, we have to validate a few assumptions. These are just a few though. So the relationship between the independent variable x and the dependent variable y must be linear, so it has to show a straight or a linear relationship in a plot. And any value of x and the resulting value of y must be independent for. So basically, any unique value of x must have the unique value of y. And also the y values must be uniformly distributed, or distributed normally. And then we also apply sum of squares for errors to estimate our random parameters beta 0 and beta 1. And so using the linear model from RStudio, we get beta 0 is to be 2.225 and beta 1 is 0.5764. And so first we're validating if this model can be the model is perfect for this data set. And so to validate, this is a linear relationship, to show a linear relationship between both variables, and looks fairly linear. We use the library to see how uniform distributed it is. Looks like a pretty linear distribution from that plot. And the nitrogen and the ammonium, they seem uniformly distributed and symmetric. And then we also see the errors using this trend scatter plot. It seems to be the error is pretty minimal, considering that the dotted red lines are pretty narrow, and the blue line represents the model. Seems to be within those narrow error dotted lines. And so we also need to test if the errors are distributed normally, and we can do this by using the Shapiro-Wilk test. As you can see, the p-value is significantly pretty high, and with a p-value of 0.509, this is significantly pretty high than our alpha value at 0.05. And you can see from the bar plot to the right, the residuals seems to be pretty uniform. And so this is the residuals versus the fitted values. This basically shows that this model will be almost perfect for this data set, considering that the residuals are randomly scattered, and they seem to be uniform towards a certain value. Uniform towards 0. And so by calling the summary of this linear model, we get to see that beta 0 to be 2.225, and then beta 1 to be 0.57637. And then we see, even though it's kind of cut off down the bottom there, but we can see that the adjusted R squared is be 0.9, and then the p-value for the intercept is being pretty high at 0.307. This means with a high adjusted R squared value, this means that this data set is perfect to be used as for simple linear regression, as well as a high p-value, saying that there seems to be a high statistical relationship between nitrogen and ammonium. Moving on, this is the regression line from the graph. Just see, this is our actual model. And so based on that line, we can say, based on the summary we had before, we can say the parameter estimates to be, with B0 is to be 2.2225 and B1 is 0.5764, which results in the model to be y equals 2.2225 plus 0.5764x, which means that for every one thing of ammonium, we get to increase the nitrogen removed by 0.5764. And then this is our predictions, and basically I use predictions of 50, 100, 150. So it looks like as the amount of ammonium added, increase the amount of nitrogen added based on those predictions. And this is the 95% confidence interval. And furthermore, we have to check if there's any outliers from some of these data sets, and we can see that there's some numbers, specifically 56, 66, and 80. And so, by removing those three values, we want to see if there's any significant differences between the previous model and this model. And it seems to me that it hasn't changed too much. It's just that the adjusted R squared values have increased, meaning that this data is still perfect for a linear regression, and the p-value is significantly high, so 0.491. So there's still a relationship between ammonium and nitrogen. So in conclusion, based on the proven assumptions results, the simple linear regression model is a good match for this data set, and that there is a clear relationship between those two, with the amount of ammonium being added and the amount of nitrogen removed. All right, thank you for listening.